Okay, so a quick review of last lecture about complex number. The most important concept is the imaginary number I, and we go over some property of a complex number like commutative, associative, distributive, and the concept of modulus. Go over the conjugated complex number and geometric interpretation of complex number and the Euler's formula. Uh, yeah, that's a few seconds summary of the last lecture. Okay, so today's lecture we're going to go over the more um, challenging part, which is so today we are going to talk about the second chapter of the book, Complex Vector Space. This chapter has a lot more content, so we may need 2 or 3 lectures to cover it. And so this is today we talk about complex vector space. So the chapter actually have a 7 unit. The first one is using the n-dimensional complex space as the example, and then go through them definitions, properties, and more examples. And then you go to the basis of the vector space, dimensions, basis and dimensions. Then we'll talk about the inner product. And the Hilbert space. It will then talk about the eigenvalue and the space. Eigenvalue and eigenvectors or eigenspace. And then talk about the Hermitian and unitary matrices. And lastly, this chapter will talk about tensor product. Yeah, that's really a lot. So I'm going to cover, I mean, 2 or 3 lectures to cover this. So, so we first with the example, the book actually start with the example of a complex number with the length of 4 or dimension of 4. And so this C4 is what? Okay, so this is C4. You have so the way you have, let me see, 1, 2, 3, 4, but each one is a complex number. It doesn't have to, I mean, it could have the real number with the imaginary, that one had a 0 in front, is still considered as a C4, I guess. And so we call that V vector. Oops, And we can also have another vector. In this case, we have what? 16 plus 2.3i minus 7i 6 minus 4i. So the first rule, well, not rule, property will be something called commutative again. So in this case, we can show v plus w. Actually, we need another one. Oops. Yeah, it is this way. Yeah. So the sum of these two metrics is kind of v. Oh, I see. There will be some confusion. I guess in most programming languages, always use I, but here the I is already used for imaginary number. So we use J as the enumeration. Here will come one more twist. In the Python NumPy, the I often use some for other purposes. So the Python NumPy use J as an imaginary number. A bit of confusion here. But you have you just have to keep that in mind. Yeah, it's because language often is customized or personalized. There are different habits or conventions to write it. We just have to keep that in mind. So, okay, so and there's then we can't you can I can just understand that as the definition or property, the way how this is the arithmetic of the complex vector is operated. So there's other way, or if we have three vector, then we have a v plus. That should be the same. And there's actually another definition. It's a bit confusing at first, but that's you have to keep in mind this is a definition of the vector. So there's another definition is called. Sorry, let me write it down. Called additive inverse of a vector. And that definition is basically a vector v is basically negative v. You may think about the inverse of matrix. That's a 1 over the matrix. And that may or may not be invertible, but for the vector, the additive definition is a minus v. So for the v at the top, the minus v at the bottom will be, we can just take everything is minus 6 plus 4, I minus 7 minus 3i minus 4.2 plus 8.1i. And this was plus 3i. Is that correct? Yeah, that seems to be correct. Okay. So this is just a lot of definition. And then we will have a v plus minus v equals what? 0, 0, 0, 0, which this is called a zero vectors. Found out on my camera. It actually goes to full screen, so I didn't see it. Oh, there are two people in the waiting room. I'm so sorry. My apologies. I didn't see people in the waiting room. So. Okay, so for student who just joined, we actually just started. We mentioned the complex vector and the additive inverse of the vector, which is basically the minus the additive inverse. We just went through this definition. So some other definition, things like a scalar multiplication of vector space. So the book basically says the vector space is the space where the addition, inverse, and the zero and the associative commutative form, that whole group is called vector space, which is basically a linear combination. That's my understanding. So, uh, so the addition will be plus, negation or minus will be negative, and the scalar operation will be a multiplication, constant times a vector. So the property of scalar operation actually is kind of intuitive. So let me write it down. Scalar multiplication. So if you have a constant C1 times C2 times the vector, and this will be the same as constant C1 times C2 and then times vector. So you have a constant with two vector v plus w, and this will be equal to c times vector plus c times w vector. Yeah. So let me summarize the property here. This actually is also summarized in the book. So to our vector operation, we have the commutativity, commutative with commutativity. That's right. So that means v plus w equals w plus v, which kind of obvious. So associative, which is v plus w, sorry, plus x equal to v plus w plus x. An inverse of vector v is minus v. And this, what are the scalar multiplication? And well, if it C1, C2, V, V. And hmm. There's actually another way, C1 plus C2. The, uh, the book actually then give some example in geometric illustration. So that including the addition. Yeah, I'm going to skip that. Yeah, basically the example to show how the two vector added up and geometrically interpreted. For example, for the v plus, so if you have a vector v, and then we have the vector which is inverse negative v, and we added them, v plus minus v will get what, 0 in the middle. So uh, and what's the other one? If there's a vector v, we multiply it, become another, this is v, and that one will be a constant times another v. So it's geometric interpretation of that. And this may look like uh, I guess all this linear combination, it seems to be a given, assuming all the linearity holds. So, okay. And then there's other definition. It's just a review. And for many of you, well, if you are first year graduates, they may still review it. The other not kind of definition is called transpose. Transpose. Oops, sorry, that's not what I mean. I mean to highlight it. Transpose. What this means, the very often is the for transpose of a matrix A is what? AT. And if basically the AT, the element J and K is the element of A's, K, and J. So it's just flipped a row and column. Yeah. That's the definition of transpose. We may just put all this definition transpose. And what this means is let me see. If I have the A, what's the, whoops, that's the black. We need a two number now, at least two. So that's A3 plus 2i, 0, I minus 6i, 1, 4 plus 2i, I, 4 minus I, 0, 4. Okay, what is the transpose of A? Uh, Well, if you look at the transpose definition, that means every diagonal when the index are the same, it will be remain the same. Basically, everything on the diagonal will remain there. So everything on the diagonal will be the same. That's right, maybe. That should be remaining there. So let's see. What can we do? Right, so 3 plus 2i, but that 0 and 1 should be flipped. 0 and 1 will be flipped. But 4 plus 2i will still be there. 4 will still be there. But 0, I and 0 will also be flipped. So, yeah. 4 minus I and 5, well, that two number will also be flipped. So this two number will be flipped. So that means the, whoops, oh, 5, oops, it's still red. Okay, sorry. Well, this is too big, too thick. Okay, is that correct? Let's see. Basically, every row become every column become every row. Is that correct? Seems to be correct. Okay, so well, this is not a big deal. I mean, oh, someone put in the chat window. I'm sorry. There's nothing in the chat. I'm not sure why there's a warning. Maybe someone deleted. Okay. Not sure why there's a flag in the chat, but then I click nothing there. So, okay, sorry. If I missed it, my apology. So this is the transpose, but there is actually another operation very important. It's called conjugate. This doesn't occur in real vector linear algebra, but in complex vector, this really matters. So this is called transpose, and then there's another definition called conjugate. Conjugate of A. And that is a symbol of A bar at the top. And that definition is basically conjugate of the each vector. So the definition of that is, oh, I didn't leave space, sorry. Basically, for every vector in the A, we take the conjugate. On the left, I said the conjugate of the matrix, and the every J's row and K's column. On the right, basically A and the J and K's element in the original A matrix, and then we take the conjugate. Yeah, that subtle difference between the length of the bar makes some difference here. So pay attention to the length of the bar here. That really makes a difference. They mean different things. So on the left, this means the J's row, J, K of conjugate of A. On the right hand, this means JK of A, then conjugate. So on the left-hand side, basically, how do we find the conjugate of the matrix of A for every J and K element of that? And we do that on the right-hand side. For every J, K element of the A, we take the conjugate. So that's basically what it means. If we really say that in English, it seems a bit confusing. So, but that mathematical symbol there is more clear. If you are used to that, you kind of follow the convention. So I'm going to highlight that. This is very important definition. So now we can combine the two. We can combine the two. This called the in the book it's called the dagger operation. It's also called in some setting it's called the Hermitian operation. I think they are the same. So I said let me I think hold on. Oh, sorry, it's called conjugate transpose, not the Hermitian. Sorry, I did make a mistake. So the dagger operation sometimes also called the with the symbol of H. I'm not sure why it's called H then. There's a bit of confusion. Okay, I'm going to just to write using the book's the definition. So the book's definition is the let me write it down. Oh, I don't have enough space. Okay, this is the advantage of electronic. I'm going to shrink this one and then have more space at the bottom. Resize. Okay, then I have more space at the bottom. Okay. So yeah. So and then the next one is called adjoint or dagger operation in the book. Which is basically called conjugate transpose. That means the for matrix like say a dagger. Oh, that's look like a plus, isn't it? Yeah, this dagger operation is not. Yeah, not look like a plus. I mean, huh. I'm going to write a different way. That really look like a plus. I'm going to follow other convention, just use the H then. H. Or conjugate or a star. Okay. So another definition is basically A's conjugate followed by transpose. Or A transpose followed by conjugate. And the definition will be for conjugate for every element J and K in the conjugate transpose matrix AH, and we will have that as K. We first do the transpose K and J, that's the transpose, and then we take the conjugate. Yeah. So and this apparently operation is very useful in quantum information on quantum computing. So conjugate transpose. So, and then the book talk about some property which we can verify. So let me see, Adam. So some property of this conjugate transpose, which is really neat. If you think about it actually makes sense. For example, for the transpose, we have a, whoops, that's a yellow. A transpose of transpose that be A itself. Right? So if we flip again, it's back. And we have A plus B transpose. And then we have that actually becomes transpose of A and B additive, add them up. And for the conjugate, we have a conjugate of A and then conjugate of A again. What is that? Yes. And there is actually a name of that's called idempotent. I don't know the root of this word. I'm not sure why it's called.
It means like not changing, Professor.
Oh, say it again.
It means like staying the same, not changing.
Yeah, but what is it? A Latin or German?
It's an English word. It looks like French, but it's an English, I think, word.
Oh, okay, sure. Thank you. Yeah. Idempotent. Yeah. So say it again.
It's probably Greek origin.
It may be Greek origin. Okay, yeah, thank you. That's certainly not area I'm not familiar with. So, okay, thanks for the suggestions. So for the conjugate, we also have this A plus B conjugate, and then will become A conjugate plus B conjugate. This seems to make sense intuitively, right? You just take the negation of the imaginary part. Here's another interesting part. Conjugate transpose. We have AH. H again. What do you think that one is? Yes, the same thing. It's called the this is again is called idempotent. Yeah, idempotent. Thank you. Yeah, I need to pronounce it. Okay. Yeah. Thank you. And then for A plus B conjugate transpose, we have what? AH plus BH. Yeah. Okay. Yeah. So, and if you put the constant scalar, is many of the property also remain. So. Now, and then the books so go down to the definition of matrix multiplication. So that's the before this is what they call I guess unitary operation, that's probably called, and then now we are talking about multiplication. So multiplication. For those of you who have taken linear algebra, this is probably kind of easier. If it's not the matrix multiplication, let me see, find a book example too. Yeah, so this is a bit complicated example. So have a so now we have matrix A times B, matrix multiplication. What's the, okay, how are we going to do this? Yeah, it's really a lot. That means that we first need to do the row and column one. So first row, I should highlight this. First row in A versus first column in B. That's how we do the first one, right? So we will have the phi. Oh, the good thing is zero. There's that zero will be, but we will have a phi time. Oh, let me change the black. So phi green again. I didn't change this. Sorry. 3 plus 2i times phi plus 0 times 0 plus phi minus 6i times what? 7 minus 4i. Interesting. Okay, this will be 15 plus 10i. And that's 0. We can just ignore it. Okay, this is quite a bit. That would be what? 35 minus 42i minus 20i plus 24i squared. Which means that's minus 1. So that means 35 minus 24, that will be 11. And this one will be 62i. Okay, so that means 26 minus 52i. Is that correct? Okay. But oh, sorry, this is a 0, 0. So that means A times B equal the first element there will be 26 minus 52i. We found the first one, and then we need to find the second one. Oh, I shouldn't put a 0 there. That's a bit confusing. I should put the question mark. How about it? Found the rest of them. Okay, I'm going to let you work on it. Oh, we could write a Python code to do that. So, I do have some Python code to see that. See whether we can. Yeah. Okay. Let's see. I'm going to share some Python code to go over this. So there, so those are some Colab Python code. That's just the first is on complex number inner product. We haven't talked about inner product. Sorry. Oh, that's for the exponential form. Last time we just to verify the Euler formula. I think I asked you to do this homework exercise, but here's the answer. So, but you should write it on your own. By the way, I actually put this on GitHub. So, let me put that in the chat room. So you could, I can also link it back to the Canvas site. I can link it back to the Canvas site. So, so complex number. I can add the, yeah, that's the first lecture. I'm saying GitHub Colab exercise. Yeah, I can put it there so it's maybe easier. So there, so very good. So it actually, if you click on that opening Colab, it should take you directly to Colab. Okay. So, which metrics are we going to do? Let's see. We have what? A is sorry. I'm trying to look at the note I wrote it. A is 3 plus 2j. And then is 0. And then 5 minus 6j. And then it's 1.
4 plus 2, right?
4
plus 2j, sorry.
2j.
And then j,
J.
4 minus
4 minus j.
0,
0.
and 4.
4. Okay, that's A. B will be
5,
5.
2 minus 1.
Oh, sorry. 2 minus j.
6 minus 4j.
4j. 0.
0. 4 plus 5j.
Thank you.
And then 2.
Thank you.
And then 7 minus 4j. And then 2 plus 7j. And then 0.
there. Okay, so now we need to do a matrix multiplication.
Mhm.
How are we going to do that in NumPy? Huh, long-term disconnect. Why did that happen? So, okay, so that should work. J is not defined. Yeah, I need to put a 1J there, otherwise it's not recognized. Still says J none. J is not defined. Oh, here, 1J, okay. Okay, so yeah, that's a bit tricky. So if we put a J all by itself, it's actually not recognized. It's recognized a variable. Oh, interesting. Is that correct? The first one is correct. Yeah, 26, 52. I hope the rest of them are also correct. Yeah. You can verify that on your own. So
So in NumPy,
Mhm.
does J work as a reserved character for the purpose of?
no, if you just put a J there, it probably think it's a variable. It represent. You could say J equal 25. Something. So put a 1J. Apparently now it recognizes the imaginary part. Yeah. It seems to. I mean, program language is dumb, so you have to follow its own idiosyncratic way to communicate. Yeah. So yeah. Okay. So yeah, I should put this one at the top because yeah. But this is actually from chapter 1. We are just doing dot product to vector. And this one is also from chapter 1. It's basically trying to verify Euler's formula and verified with the trigonometric form. They are identical. Yeah. Uh, so I should move this down because that's the next. How do I move this down? Yes. Yeah. So let me add another part. Here's the example of a complex matrix multiplication. But how do I save this? And I can just save this back into my GitHub, and it will be updated there. So complex matrix multiplication. Added there. So it's a bit slow. That's because Google is cutting costs. Google used to be very fast, Colab, but apparently because of the economy, whatever, Google
We
is.
wanted everybody to use it, and then everybody started using it.
It could be more users using it. Yeah, I mean that's another way to put it. Yeah, but in any case, its service is slower than before. It used to be really fast. When working class is almost.
Maybe you can choose to run in the GPU. Would that be faster?
But this is not GPU.
I know, but if you choose a GPU, maybe it will run fast.
Probably not, because I'm not using the code is not taking advantage.
Oh yeah, you're right.
Yes.
That's not going to be sufficient way of using it.
Right. I mean, if I want to use GPU, I need to take advantage. The code is parallel. Yeah.
That's what you get, but parallel overhead will probably make it.
Yeah. But
it's slower than just running it on the CPU's.
well, to be honest, if we run the code in the GPU for just 3-dimensional matrix, it's probably still slower than CPU anyway. So, unless you have thousands or dimensions there, so you probably make this probably won't make a difference. Okay, so that's it's good. We have the Python. Yeah, in a way, our arithmetic capability is probably degrading in a sense, but it's convenient. Yeah, so it's good. Like a manual calculation with the first one is still correct. So okay, but I'm not going to do the rest of it. You can work on your own to verify whether Python made a mistake or not. Okay, so let's move to the next part of the. We can actually verify transpose, conjugate transpose. Do I have a actually that's the next exercise which I just moved downwards. Yeah. So and then there will be the matrix is also associative. Let me write it down. I stopped sharing my iPad. Let me go back to share my iPad again. Yeah, iPad's still not convenient to run Colab, but the Node is very convenient. So okay, so matrix multiplication actually is a bit tricky because it is not necessarily follow the vector linear, because matrix you need to follow its dimension. So that means A times B not necessarily means B times A. So unfortunately, that actually doesn't work here anymore. So we have for multiplication, we have A times B times C. This is actually still work. That is the same as A times B times C. But A times B and B times A can mean different things. So B plus C times A is also means B times A times C times A. This is also interesting. Depends on whether you think it's intuitive. So the A and B matrix product transpose is equal to B transpose times A transpose. It's not very intuitive, but that's the property. So we also have the conjugate. And this one actually still following the same order. And then we have the conjugate transpose. Yeah. The matrix multiplication rules or properties, not rules. So. The book actually have a lot of exercise for this part. It talk with these rules, then we have the so-called complex vector space, which is a linear map, basically. So-called that's not it. Which is basically linear of the vector transformation. So okay, so, and then with that, actually, it now talk about the basis of the vector space, basis and dimensions. So this is actually quite important because many of the quantum computing transformation gate will use this concept. For this one, we need some definition called what is if it's a base vector of a space, that means all the base vector has to be something called linear independent to each other. So we need that definition of the linear independency. Base vector, they have to be independent to each other. But since they're going to, the combination of those base one need to represent the entire space, all of them have to be independent. Apparently, the definition of that is all the sum up, and so v0, all this vector sum up is basically the zero vector. If all their linear combination sum up, that set of vector is considered a linear, is a definition of a linear independent. This is not proper, this is just a definition of that. So this is, you think about it, it seems to make sense, right? So if we have the vector 0, 1, 1, 0, because they are all independent. If you want to sum up into 0, you have to put coefficient on 0 there. Right? So Yeah. Basically, all the C and J are 0, then it will be 0. It also means the vector, each vector cannot be a combination of other vectors. Each base vector cannot be a combination of other base vectors. Yeah. So there are also like a canonical basis, and basically the dimension is 0. That would be the canonical basis, but there are also transforms. And another concept here, which is quite relevant to quantum computing, is the transition matrix. Transition matrix. So from it basically change from one base matrix into the other base matrix. It's called transition. Change from of basis matrix to another one. Change of basic matrix to another one, to another basis matrix. So let's see, the book gave you example of a transition matrix of 2 minus 3 So it had the that means had a vector. The book gave a example of a vector B 2, 3. And then it goes to another base vector. Minus 4, 3. I got a 9, is it not? So that's 6. This is 3. 6 plus 3 is 9. Yeah. Okay. And 3 minus 9, 5 minus 4. No. Minus 9, 5, minus 14. Sorry. So so the important transition matrix in quantum computing is this matrix. Marder matrix. Oh, this can be a bit confusing because this also often replaced by H. Let's just well, this is letter H, not the superscript. Okay. So the Hadamard matrix H is which can also be right like and that's the often implement at the gate in quantum computing. And now the question is whoops. On the top?
Yes, up there.
You mean -9?
Yes, so it would be -6 minus -3.
Probably not.
Oh, is that? That's the closing.
How about you write the Python code to verify whether you know?
It looked like -3 there.
Oh, you mean here? I says no. This is yeah. So that's okay. Yeah. My handwriting is terrible. Now, the question is Hadamard's matrix times Hadamard matrix. What is that? What do we got from that?
Is it identity methods? 1001?
Is it? Is that what we got?
I think so.
Okay, let's see. We can write a Python code to verify this. So who has tried the Python code to verify that? Oh, I closed my code. Where is that? Oh, I found it. Okay. So this will be the Hadamard code. And we can just use the 111 and to see how that. Oh, sorry, I wasn't sharing the right screen. One, one, -1. Yeah. I have an error somewhere.
I think you're missing a square bracket at the beginning. Yeah,
Oh, yeah. Let me
and
check.
then here also at the end.
Okay. Oh, I guess I need to put that.
1/square root of 2.
Yeah. So, but if it's 1 square times 1 square, that will become a 1, 1. So, yeah.
Yeah, I was right. You said I don't.
So,
1, 0, 0.
yeah. How do I put the 1 square over there?
And there's a functional square root.
I'm trying to see the Python library for the square root.
I think it's np.sqrt
Is that the
square root. I think so. Let me see.
oh? Can I put in the chat window?
Let me make sure about it.
Oh, let me see. np dot the square root.
Yeah. No.
Oh,
Yeah.
correct. Okay.
Yeah.
Probably put it outside. That works. No, it didn't work. Although there's another way to do this. Apparently, in some there's another package. There's a directly. Oh, that's still that. We have to normalize that. That is correct, but np dot dot is. Oh, I know, because that's considered a 0, so that is correct. It is so small, it is 0. Sorry. Yeah. Sorry. I thought it's wrong, but apparently that's just a numerical.
Yeah.
That is 0. It is correct. Sorry. Sorry. Took me a moment to realize that is correct. My apology. Okay. So then, for a moment, I thought Python had an issue here. Okay. So that is correct because it's so small. It is actually is 0. So it is identical magic. So, oh, sorry, I ran out of time. Yeah. Okay, but let's do a quick review of today's. Let me go back to my notepad again. So we just really covered a lot. We mentioned additive inverse of the vector. And we mentioned the matrix multiplication, complex matrix multiplication, transpose, conjugate transpose. Potent property of the conjugate transpose and the conjugate matrix multiplication property and base dimension and Hadamard matrix. Okay, that's really a lot. I'll see you next time. Yeah. Try to work on some Python code yourself and see how it works.
All right.
Yeah.
Thank you.
Right. Yeah.
Bye.
What's the library that you use to represent the Hadamard matrix?
There's a few.